Great. Okay, so welcome back. If you've been here before, my name is Megan Fitzgerald. I'm the current product manager of the platform team. And on this developer community meeting, we're going to be discussing ACP-83, which is introducing the idea of multidimensional fees and a dynamic fee to the PNX chains on the primary network. This was authored by Alberto Bengiamo. And Steven, Druba, and the rest of the platform team have also been actively participating in the discussion, Aaron as well, to spec out the design of this. So I'm going to let them take it away. And this is an open discussion. This is meant to be active discussion. So if you have any questions, please post them in the chat or in the question section in the bottom right of this screen. Or if you have any questions after this meeting, I highly encourage you to post those in the discussion board on GitHub. All right, go right ahead, Alberto.
Yeah, I'm going to share my screen. Can you guys see it?
Yes.
Okay. So, hello everyone. My name is Alberto. I'm an engineer from Milan, Italy, and I've been with the platform for 3 years now. So I wrote down this ACP-83, which is a proposal to bring dynamic and multidimensional fees to the P chain and the X chain. And the ACP has been out there for maybe a month or two now. It was pretty quiet. But lately, discussion has come up essentially because this proposal intersects in interesting ways with another important project that we have, the ACP-77, which, as I'm sure you know, focuses on essentially restructuring the subnet with the idea of bringing down cost, increased customization, and in general, make it easier and more economical to spin up a subnet. And so this is a place where we can go over the few of the open points that are around these intersections, and more generally, we can go through the ACP and maybe tell the way we think about this. Feel free to interrupt me anytime in case I'm not clear or anything. And so the idea is that I'm gonna go at high level through the ACP. I'm not gonna go into much math, but just list the main ideas and principles that we're gonna use to introduce dynamic fees, and then we'll have a discussion. So I think that the timing is very interesting right now. As I mentioned, the ACP-77, which is authored and led by Artruba, is going to change a lot the way we do subnet. It's going to probably be the most important, piece of change that we're going to work on in the next fork. And so we do anticipate an increase in general, an increase of activity over the network. And the idea of dynamic fees and multidimensional fees is really to have stability of the P chain above all. As I'm sure you know, P chain do tracks a whole bunch of ecosystem metadata, what subnets are there, what chains are there, what validator sets are there. And not just that, the P chain is a key component for our cross-chain communication protocol work, because essentially, in order to verify that a message is reliable, a subnet is gonna, retrieve the validator set of a given of another subnet, and sort of check that the message was duly signed. And that's what the P chain comes in, right? In providing this validator set. The P chain is also very key in the way we do block building, essentially. We do have this snowman plus mechanism that sort of orchestrates who can propose a block, at least in the primary network. And again, there, the idea is to retrieve the validator set at a given height and assign a slot to proposed block at every validator. So the P-chain is key in a lot of these operations and protocols. Is mostly read than written, honestly, but we want to make sure that it's going to stay stable even if the activity over the P-chain go up. And as I'm sure you know, the ACP-77 is going to move a lot of logic out of the P-chain into the hands of users. And so it's even more important that we have stability. The X-chain is probably less relevant. I'd say it's the least loved primary network chain that we have. Used to be a DAG. We linearized it as of Cortina fork. But I'd say basically introducing the same kind of fee mechanism over the X-chain as a very low marginal cost. Once you do it for the P-chain, it's very easy code-wise to have it over the X-chain. And so proposal targets both chains. There are two main aspects to these proposals. So one is the dynamic part and one is the multi-fee part. Actually, one of the open points that I think it was Aaron to raise publicly is around the scope of the next fork. I'd say now, but we can go back later about this, that probably the dynamic part is what's really very relevant to us. The multi-fee part, we can sort of delay it a bit. But again, this is open for discussion, and we'll probably tackle it later. So I'm going to go about the multi-fee and dynamic fees. I'm going to go through the multi-fee part first, which is so the work around the multi-fee really, there's not much new. A lot comes from the experience that Patrick built up with the HyperSDK, because the HyperSDK already have its own way to do multi-dimensional fees, and also a bunch of research on top of it. The idea of multi-fees is essentially that whenever you verify and execute the transactions, there are a whole bunch of resources that are touched, and they are not necessarily homogeneous. Now, what the resources are is really chain specific. In this proposal, I listed 4, but we know already that the ACP-77 is going to iterate on top of this. Nonetheless, it's the structure here that matters. So point 1, you have different resources with different features, maybe different cap, different different amount of resources that can be consumed block by block. What I propose here are like 4 of them. These are really bandwidth, CPU, and sort of disk access in read and write. So when you verify and when you execute the transactions. And the idea instead of having like a single accounting unit, like a single gas unit per each of them, is to have multiple ones. So the idea is to specify a way to meter all of these resources separately, to specify a fee rate per each of them. As you see here, fee rate is really how many AVAX or how much nano AVAX I should pay per unit of bandwidth, per unit of disk access, per unit of CPU, however we meter them. And then have a fee that is really, as you see here, it's really the scalar product of these 2 vectors, right? So you have complexity, you have fee rates, and you get the scalar product, and that's the minimum fee, let's say, that you're supposed to pay. As I mentioned, the ACP-77 is most likely going to add a 5th dimension on top of this, which is the validator set. And so again, we wanna make sure that an environment where subnets control their own validator set. The validator set occupation and activities is fairly priced, and it's probably going to have its own dimension. But the idea is that different resources and different fee rates per each resource. The idea is that, or the intuition is that economically, if we allow these fee rates to vary independently from one another, we're going to have more efficient. So we're going to have, let's say, fuller blocks with less amount of fee overall paid. So that's again one point. There is a drawback, or if you want, a complexity dimension is going to be introduced by this multi-fee. And I think Aaron was the one who pointed out publicly first, and is that both the transaction building and the block building gets slightly more complicated as we introduce this feature. On the transaction side, the idea is that right now we have a very low and fixed fee. So whatever you include in your transaction, doesn't matter, you're going to pay the very same fee. And this actually allow historically stuff like this one. So I've indexed our mainnet while I was working on some simulation, and this is the most complex transactions that I found. As you can see, it's an export transaction that moves something like 7 million AVAX in one go. And it has two outputs, but it touches something like 1,300 maybe. Yeah, so 1,300 UTXOs. In a multi-fee world, this is a transaction like that will probably not be feasible anymore for a couple of reasons. One is that we're gonna impose some kind of cap on resources. The cap will be different resource by resource, but we probably are not going to allow 1,300 signature verification in a single block, because that effectively would cause a node to sort of have a 100% CPU usage on a single block and sort of stall any other activity, any other validator query service that the P-chain needs to do. That's one point. But even if we set the cap so high that this kind of transaction is still allowed, there will be a cost in adding the UTXO. So when the fees are fixed, you add an extra UTXO, doesn't matter. But when the fees are like related to how big the transaction is, an extra UTXO is going to cost some extra bandwidth, some extra CPU for the signature verification, some extra state, and so it's going to cost. And so transaction building becomes some kind of knapsack problem when you're going to try, to pack as much value as possible with the lowest, let's say, space of occupation or complexity. And so the transaction building algorithm is gonna be slightly more complex, at least. And it's nothing super new, say computer science wise, but it's something that needs to be accounted for. That's one complication. The second complication that I think also Aaron pointed out is around block building, really. So we're gonna, as I mentioned, we're gonna place some caps about how complex a block is gonna be, and these caps should be reasonably high. So for normal operation, we basically won't see these caps. But if for some reason the P-chain mempool becomes pretty full, there is a surge in activity that continues maybe despite the dynamic fees that we will see. The block builder will need to decide what's the next transaction to include accounted for these caps that we don't have right now. And it's not super easy to, I mean, again, it's a multidimensional knapsack problem. We have heuristics around, but it's a complication to account for, given the schedule that we have for forks. Yeah, and so it needs to be accounted for. I think that's pretty much it for let's say the multi-fee part. If there are no questions, and again, feel free to interrupt me anytime, I'd move to the dynamic fee part. I can't see my. I'm gonna. Yeah. Well, sorry, I cannot really see that.
That's okay. Sachi just said it sounds like a graph problem.
Yeah, again, nothing super new, but it needs to be implemented, and also the mempool must be maintained sort of order at the very least. So that's part one. Yeah.
Just to clarify, does that mean that the plan is to separate this ACP into two ACPs, one with the multidimensional component and then one with the dynamic fee component? Just wanted to make sure, just to clarify.
The way I see it is this one of the open points. So the ACP might stay as one, but when we actually plan the delivery, we might sort of deliver first maybe the dynamic part and then deliver a smaller version maybe of the multi-fee part and then iterate in time. That's all I meant. I don't plan currently to split the ACP, but in sort of implementation wise, there won't be necessarily a straightforward one-to-one mapping. That's what I meant to say.
Okay. I think we probably want to, like, if we actually like activate like some portion of this, then like that probably should be factored out into this explicit ACP, just so we're super clear about, you know, like when validators are like signaling on what they support and things like that. It's very clear what exactly is going to be activated, but we can maybe flesh that out. Yeah.
Sure. Okay, multidimensional fee. If there are no questions, I'll move to the dynamic part, which probably even more interesting, it is to me. And so the idea here is that we want to have responsive fees, meaning that if there is an increase of traffic over the P chain, we want to make sure that these fee rates increase and they go down again when the load is not that much. Now, again, this is hardly a new thing. There are also a bunch of other chains that do apply this kind of mechanism. But it's not so trivial to devise, let's say, a precise fee scheme and a precise feedback loop. I want to go real quick through a proposal that is not ours, but it's something we look at when we were doing research. Oh, so sorry. Where am I? Okay, I lost it. Oh, here we go. So this is an early proposal of the EIP 1559, and I mean, it's a scheme that we considered at some point. The idea is that you're gonna change the fee rates or the gas concepts are similar in a multiplicative fashion. So at each block you will have a fee rate, and at the next block you're gonna either increase it or reduce it of a factor that is the one described here. And it's a factor that depends on the complexity target that you have. So if the complexity of your block is above the target that you specify, you're going to increase the fee. If it's below, you're going to reduce it. And that's it. So the idea is that this should drive users to be around the target that you plan to enforce. The thing is that you can show mathematically. I mean, it's pretty simple, but I'm not going to go into mathematics. That's not the case with this specific kind of scheme. The reason being at a high level that if it happens that users generate block that whose complexity oscillates around the target, so you might have smaller one, larger one, but on average you are around the target, you would expect the fee rate to also oscillate around some kind of stable values. But what happens is that actually the fee rate go down, or in another word, so say symmetrically, if you sort of if you strive to keep a given fee rate and you create larger or smaller blocks trying to sort of pay roughly the same fee rate for each of them, well, what you ideally would like to have, like the target, and what actually you will have diverge. There is like a tracking error where the target is going to be increasing in time linearly, but the actual blocks generated, again, they will oscillate, but all in all, they will go up faster than that. Again, this all comes from this inequality here, but it has been shown also in simulation and measurements. And that's why we're not going to use this kind of scheme, but we took care of using, I don't know how clear this is, using some kind of exponential update scheme. And so let's see if I can describe it without drawing you in mathematics. The idea is that we're going to track on one side the cumulative block complexity, so how much complexity is per each block, say, since the beginning, and then the ideal one, so how much complexity we would have liked to have instead. And these are not necessarily the same, but of course we want a fee mechanism to strive to push them close together. And the idea of our fee mechanism, the proposal here is that we're going to track this difference between the cumulative amount of complexity in a block and the target that we wish we had. And we're going to have a fee that goes exponentially up with this difference. So if our blocks are more complex than we would ideally like to have, or blocks are not that big but are generated very fast, so that's also another dimension of complexity, right? You have sort of small blocks but very frequent. Then the fee is gonna go exponentially up with the complexity, and vice versa. If sort of the blocks are generated more rarely, they're more spaced in time, or even they're not generated at all, so the chain quiesce is silent. Again, the fee are going to go exponentially down till this minimum floor that we're going to introduce. And so, okay, the mathematics here is slightly complex, more maybe complex than the ideal, because we have the max here that accounts for both the activity period and the silence period. But the idea here is really that at every time we update this cumulative excess complexity, that is the complexity that you have plus the complexity of the extra block that's coming minus the target. And essentially, we're going to express the fee as the exponential of this complexity. That's all there is to it. I've been working on some simulation here. Yeah, they're here. So what I've done is really index the chain, the P chain over mainnet, and sort of come up with just peak periods. So this is actually a real peak that happened. These are a bunch of blocks of pretty large export transaction, I think, that happen all at the same time. So you see them in contiguous block because I'm plotting heights, but their timestamp was not moving. They were really close in time. And I show here how an exponential algorithm would behave. Of course, we don't have the feedback mechanism. We don't have historically people backing off. But at the very least, you see here that you have the fee rate going from a few milliavax, they're close to zero, to so as the peak continues to go on, the fee are gonna go up until say tenths of AVAX, and that's like a 10,000 increase, right? But then even faster, as soon as the block stops and complexity go back down, the fee rate go down even faster. So that's a property of this exponential update, and this is something that ensures that the tracking error is contained.
To be clear about the fee, you mentioned earlier that the large export transaction with like 1,300 inputs probably won't be allowed, like based on the maximal limits that we want to place on the primary network. So the fee that you graphed there is the historical state, but I don't think that is a fee that people will actually see in practice, right?
Yeah.
Like just because we'll have a maximal complexity. Okay.
Not just that. So in here, really, this, if you want, this game theoretic feedback loop where so there are essentially no users that are observing high fees and withdrawing. I'm really using the traffic that we used to have that doesn't factor in the effect that the fees are going up. And so what is likely to happen is that people are gonna sort of withdraw their transaction issuance much earlier, so much before we reach this amount of fees. What this is for me, what the simulation is useful for me, is a way to tune the update parameter formula here, because here you have a bunch of parameters like the minimum fee rate and especially the denominator that controls how quickly you react to an increase in complexity. And it was a way to come up with a reasonable estimate. Now, I think Aaron voiced some comments around, precision of using past performances sort of to size these kind of parameters, or to size like future behavior. And I think he's right in many respects, like especially for these dynamic parameters. Like in the past, we had different forks. We had periods of larger activity and smaller activities. So you got to be careful in the way you do comparison. And I think a way to tune this kind of parameter is probably benchmarking, right? So on a sort of average node, let's see how much time it takes to verify a signature or a larger and larger transaction, and sort of go from there rather than look at historical performances. So I think for caps, for how big the maximum complexity should be, probably the historical usage of historical simulation is interesting. Probably for this dynamic parameter, as you mentioned, that's not the best. Benchmarking is the best. We cannot anticipate, people reactions as easily. We probably need some kind of simulation with some intelligent actor. And I think internally, Maru probably proposed some kind of test like that. But yeah, to go back to your point, it's likely that we won't see anything like that in production, because these are really people pushing their transaction out, even if the fee rate is going to go up 10,000 times. I guess that's unlikely. And that's all I have really for general description of this proposal. I'd say there are two main. I'm gonna stop sharing now. I just say that there are two main, say, open points that has come up so far. I think Aaron brought them up publicly, but they're shared internally in our lab. So one is, around the more complex block building features and how exactly to behave, especially when you are a cap, right? Like the average usage should be all right. We shouldn't have fully, filled blocks. But as soon as we start maybe hitting fully full blocks, what transaction should go next becomes a non-trivial decision, and there are algorithms and heuristics to play with. And it's important that we ensure there are also sort of Byzantine fault tolerant, let me say. That's one point. The other point is
I don't quite understand the BFT tolerance, like part of that. Like if every node is building blocks based on their own like block building algorithm, I don't understand like why our block building algorithm needs to be like Byzantine fault tolerant, because everybody's going to propose a block based on Snowman++, right? like, I guess you want virtuous nodes to build blocks optimally, which is obviously like what we're going to do. But I don't see how we can actually make a like algorithm that's BFT if everybody has a different view of the mempool.
So probably BFT was not used scientifically there, but what I mean is that we should be, so these different fee dimension and the presence of priority fees that I didn't touch upon, but they force us to somehow order the mempool in a certain way and to keep it ordered. And so we got to be careful just to, make sure that a node doesn't drone into try and keeping this mempool sort of order. And the mempool is sort of it's weaker somehow in the actual blockchain. So, transaction can enter and go, and we just want to make sure that we have an algorithm that doesn't, force a node to waste cycles. Just trying to keep its mempool order. That's more what I meant. Really.
Sashi, you can go ahead.
Yeah. Droba, I think that the BFT portion here would be that when we want to do any validation on the proposed block, right, we want to make sure that not only we accept it, but we accept it and we validate that it doesn't violate these resources constraint that we were expecting the block builder to apply, right? Because the block builder is super powerful, right? And they can order the transaction as much as they want, and they can pick and choose whatever they want, right? And there are multiple valid options, right? And that's perfectly fine. The validator need to make sure that when they do make that choice, that option, that one of these valid options truly align with the restriction that we put. And I think at that point, it would be a BFT compliant.
Well, if I'm a block builder and I just build a block with one transaction, like that's my algorithm. I only fit one transaction into the block and I don't try to pack any others. That's a valid block, right? It's not the optimal block because maybe you can fit more than one transaction in the block. But if I'm like trying to slow down the network and it's my turn to propose a block, I could just only pack it with the minimal amount of transactions. And that would be a valid block. So I think like what we're really trying to optimize for is not like the Byzantine case. It's like in the virtuous case should be building blocks as optimally as possible and as full as possible. So I think it's literally just a multidimensional knapsack problem. Steven, I saw you unmuted a few times. So do you want to?
Yeah, so specifically the concern here is not a Byzantine block producer or whatever. It is that you have malicious clients attacking a public block building algorithm because Avalanche goes block building, code is going to be public. Can people modify this? Yes, but like many people do not. So the specific thing is that we want the public block building algorithm not to be attackable by clients, like user initiated transactions, specifically in such a way that the blocks are packed so poorly that it impacts the fee mechanism itself, right? So Aaron, I think, talked about the attack where like, well, let's say that you run out of compute, but everything else is underutilized. So now the fee decreases for those other dimensions, increases for compute. You now issue a different transaction type that maximizes some other dimension, and then you keep switching back and forth, never paying high fees, and like causing the chain to essentially become not useful. So I think that's the specific thing here. It's about the robustness of the publicly available block building algorithm against maliciously crafted transactions. So this is not necessarily as much of a concern in like a single dimensional case because you can just essentially greedily pack your block, and it's very easy to see that you can't game across different dimensions if there's only one dimension, right? So the main thing with the multi-dimensional like Byzantine environment isn't so much the Byzantine validators, but it's like malicious clients. So that's specifically the concern with like multidimensional block building. So yeah, I don't know if that answered the question on like the concerns with that, but.
Yeah, it did. I think the other thing I had concerns about was the priority fee inclusion in the ACP with the P chain and the X chain. Just as a refresher for everybody on the call, like they're UTXO based chains, right? You're effectively committing to what fee you're going to pay during transaction building and signing, since it's just the number of outputs minus the number of inputs denominated in the box. So there's no real, like, unless we decide to change the chain transactions, which I don't think we will probably do in this ACP, there's not really a space for a quote unquote priority fee, since you're just committing to the max fee you're willing to pay, which is a single number. So what we could do is use the base fee or the minimal fee that is computed through the dimensions, and then any excess is the priority fee. But there's no real notion of like updating or like committing to a priority fee during transaction building. At the time of your transaction getting included into the block, only then could we actually compute a priority fee based on the fee you've committed to minus the minimal fee your transaction has to consume. But I'm not too sure how exactly we would want to order the mempool based on a priority fee that's changing per block.
So this is again like a single dimension versus multi-dimensional kind of like nuance. In the single dimensional case, you can just order blocks by, or order transactions by the fee paid divided by the complexity, and that will result in ordering by your priority fee. The issue is more in the multi-dimensional case where that's not necessarily true anymore, because now you have this single fee that's being split across multiple dimensions, and you don't really have a priority fee per dimension. I think that, again, that's a bit of just a complexity. Like, we could definitely have a notion of prioritization based on fee in the single dimensional case. In the multi-dimensional case, this is again touching on the block building of the multi-dimension, kind of why it's complicated, I would say.
I want to make sure that we give ample attention to the dynamic fee discussion while we're here. We have about 20 minutes left, because I know that obviously there's still a very open discussion between single dimension and multi-dimensional fees when it comes to block building. But one thing I did want to ask Alberto or anybody else on this call who has an opinion or has good facts to back it up is what evidence exists to suggest that an exponential fee update rule for the dynamic fee actually provides greater stability when pricing that base fee per block? You know, maybe Alberto can elaborate on some of the work that he showed us earlier, or anybody else could pull from their own experience potentially.
Yeah, so for me, it's really this inequality that I showed before mathematically, but I can try to give an intuition around that. And the idea is really, if you so what happens is that, let's say as a block builder, I try to package as many transactions as I can while keeping this fee sort of constant, maybe not minimal, but sort of around some kind of target. So what I would have to do is somehow oscillate, have blocks that are slightly smaller and then maybe slightly larger than my target, and oscillate sort of back and forth so that on average I'm around target. And the thing is that with this kind of exponential update, if I do this, sort of the contribution of when I'm below target and above target cancels out very, very neatly. I mean, this happens mathematically. But with other kind of schemes where transaction where the fee is not increased exponentially, That's not the case. What ends up happening is that I'm gonna sort of pay a bit more for a large block. I'm gonna pay a bit less for a small block. But overall, when I pay less, I pay less than what I pay when I pay more. I don't know if I'm making sense here, but essentially, the two contribution above and below target, they don't cancel out exactly anymore, and the error goes towards the larger block. So what happens is that if I have a network where I have, again, larger and smaller blocks, sort of just trying to keep the fee rate constant, what happens is that I will have some kind of target, but the actual total complexity of the block that I produce will go up more than that. And so I will end up with more and more load that is not correctly priced, because the fee rate won't change, but I will have larger and larger block eventually. I'm not sure I can be clearer than that without going into mathematics. I'm not sure if this answered the question. But
I think something to note for
go ahead.
Just something to note for the dynamic fee algorithm that's written in ACP-83. It's a very similar algorithm to the one used by ETH for Blobcast. I think it's EIP 4844. So we're tracking the excess amount of complexity over time, similar to how ETH tracks the excess number of blobs over time to calculate the fee. We apply it to a multidimensional setting in the ACP. They're only applying it to the Blobcast setting. But I think they have a ton of research showing like why exactly that fee mechanism was desired.
Okay, great. Thank you. I think that there's a question in the chat from Erwin. He says, why would a proposer spend this effort in solving the knapsack problem if the fees will be 100% burned in a current implementation? Why wouldn't a proposer do what Druba is saying and be done? In fact, slowing the network and making the fee smaller, since blocks will be of low complexity in the multidimensional case.
For the last like 5 minutes, I've been typing up a response to that, so I think it screen. So that isn't necessarily so. The first part of the question, why does a proposer spend this effort solving the knapsack problem? Like, this isn't really a change from the existing mechanism, right? Like, blocks are still not, like, fees are not paid out to the block producer currently, whether it's on the P chain, X chain, or C chain, directly via the protocol. So this mechanism as a whole really isn't changed at all in this ACP. If we were to want to change that, that is a conversation that could happen. But I just think like status quo, this isn't actually like a change. As far as like the rationale on why this might not be needed in the first place, is essentially like you're trying to incentivize people to produce like blocks with transactions in them. There's really not like, in my opinion, like, I don't think you need to incentivize every aspect of the protocol. It's essentially my like high level opinion. So if you look at like just the mempool in general in like any blockchain, participating in mempool gossip, sending transactions around is not incentivized by any of these protocols, but this is still something that's done by many nodes. Running non-validator clients is not incentivized, but it's still, you know, something good that, you know, helps nodes bootstrap, helps like things happen, you know, so like there's a lot of parts to these protocols that aren't strictly incentivized. It is true that in most other protocols like Bitcoin, Ethereum, whatever, like there is a much stronger incentive to like well pack your block to maximize your fees. But like I don't necessarily agree that it should be taken like at face value that this needs to be incentivized. If you're someone that has a large amount of stake in the Avalanche network, you're probably incentivized for transactions to go through so that the network is usable, right? So just implicitly in that mechanism, like you want the network to be like performing well. So that's kind of like the original kind of like thoughts on why this might not be needed. So I think that it's totally a fair conversation to have on if there should be that mechanism, but I just don't think it's necessarily important for this conversation because this isn't changing that mechanism. Yeah, so I don't know if that answers the question fully. I know that that's mainly my opinion and some just historical background, but I don't know if okay, there's a follow-up question here. It depends on how complex, less costly this protocol becomes. I think that that's a big reason why we're talking about like the design of the thing. Like we're not going to actually be running an NP complete thing where, you know, you have to spin up a server farm to like pack this block and then like ship it out. Like that's very unreasonable. So I think that's one of the big reasons why there's interest to separate these two mechanisms out so that we can focus on the dynamic fees portion and also then separately focus on the multidimensional, just because it is much more complicated on the block builder. But again, like I don't think it's necessarily like if there is a protocol that works that solves our things in like a reasonable amount of time and like your node isn't like spiking in CPU usage when it's your time to build, then there probably isn't a huge incentive to modify your node to like not produce these or not perform this algorithm. So I think that yeah, that's the thoughts here. Like I think the hope is that we would come up with an algorithm that doesn't require solving a knapsack problem. Yeah.
I think there's a lot of protocols that we can look to for inspiration here. One that we pointed out in our earlier discussion, and I think on the GitHub discussion as well, is DRF, which is Dominant Resource Fairness. That was introduced by Databricks back in like 2010, I think. So pulling on some of those threads for like scheduling from databases could solve our problem here. But as Stephen and Aaron have both mentioned on this call and on the GitHub discussion, like it is less trivial of a problem than like just doing FIFO, which is what we're currently doing on the P chain. And in terms of timelines, my personal opinion here is we're probably going to have a pretty a longer delay between testnet and mainnet activation for like this next fork, just because of how expansive ACP-77 is for subnets and just in general, like how large the change is. Since it's like a block building thing and not like a block validity thing, I don't see why we wouldn't, like if we come up with a protocol we're happy with but maybe don't have fully implemented, we could probably be okay with going to testnet with just FIFO for the multidimensional fees and then introduce the block building prior to mainnet activation.
Yeah, I agree. Definitely.
So we don't necessarily have to like split it into a separate upgrade just because it's a change on the block building algorithm rather than like something changing on the block validity side.
Are there any outstanding questions, or does anybody have any opinions on what Drupa just said about not including? Do you guys think that it should be included in the same upgrade, or do you think, you know, if we get everything that is outlined in ACP-77, like fully fledged out, tested, ready for mainnet, that we are going to want to wait for multidimensional fees to be implemented on the P and the X chain before pushing that upgrade?
I think like the multidimensional fee complexity is really worth it when you plan to have like a pretty constrained usage of capacity. I would argue that we're like on the other side of that spectrum right now. So I feel like we could get away with just having a basic dynamic fees mechanism without it really like impacting much. But then as subnets continue to gather in popularity, that we could transition into a like my screen's freezing, so I don't know if you guys can still see me, but we can transition into like maybe more of something that more accurately accounts usage to like better drive or better pack or better utilize the capacity assigned to the P chain. So long story short, I'm like, as someone that is super into multidimensional fees, like I'm very interested in seeing their like continued rollout. I'm not sure that it's worth the complexity at this exact moment, given the other efforts that are currently underway. So that's my short retort,
I also
maybe.
personally feel that it might be easier to plan and design once we see activity from permissionless subnets present on the P and the X chain, right? Because it'll be more clear like what resources will be more in demand, which ones will be less in demand, how to properly price those, et cetera, after activity has begun to exist on the network.
I'd actually say that's not really true, just because it's going to be related to the actual capacity of the network as opposed to demand is sort of the whole idea. So I'd sort of disagree there, but definitely agree with Patrick that there's not really a clear need for multidimensional fees now. It seems, like the reason we're sort of going towards this is because, one, we don't want to have fixed fees forever. And also the reason we're particularly motivated to do it now, we've wanted to have dynamic fees for a long time, is we're sort of starting that in order to have a strong design for the continuous fee associated with ACP-77. And we've started all of this work of saying, well, we want that to be dynamic, which is largely because we don't want to launch ACP-77 only to have a future upgrade force everybody who is using that to actually have to change their contracts, change their programs, because we want to commit to that interface. The nice thing about the design for multidimensional fees that we have now is that it's not going to have any impact on that interface. So we can very easily move it into a separate ACP, move into a future upgrade without worrying about forcing that change on users who have assumed there's going to be this long-term interface. So I think it actually works out really nicely. It's super interesting work, and even fixed fees have actually been fine for us. We don't want to have them for a long time, but it's been okay. So I don't think there's really a need to have a more like dynamic fee algorithm even for like usage on the P chain. I'm actually not too concerned about it, or any more concerned about it than I have been. And I don't think the need is there for multidimensional fees right now.
I mean, I think the context too for the group in like terms of our like previous conversations around this was my hope in asking Alberto to like really dig into this was that we could speed run the dynamic fees trek and just like not actually have this intermediate point of implementing single dimensional dynamic fees. But when you do that, I think the reality is that most of the multidimensional fee stuff is still pretty cutting edge, and like some of the common problems are still very common problems, is particularly around like the packing problem. And so when it comes to usage of our resources, it feels like just pushing harder on the ACP-77 and getting out of the way is at this point the right thing to be thinking about, rather than thinking about more complex fee packing semantics. So yeah.
I think to be super clear about like the ACP-77 part of this, and somebody did ask this as well in the chat, so I'll just read it out. Erwin asks, as I understand, multidimensional will be useful as a way to add subnet size for the fees paid to the P chain by these subnets as a way to do pay as you go. Is this thinking correct? Sort of. Like, we don't actually need multidimensional fees to do the continuous fee on the P chain. We really just need, for pay as you go in particular, we just need an algorithm to actually compute the fee. And that algorithm is already pretty well specified in ACP-83. So we'll likely update ACP-77 with that algorithm and provide the parameters for what the fees should be. This means that like, even if we do single dimensional fees on the P chain, like we'll still be able to do pay as you go. It's not required that we have to like split it into bandwidth, DB reads, DB writes, and compute to actually implement pay as you go.
Yeah, the way that I've been thinking about this is like we have these multidimensional fees for the transactions being actually executed in the block, and then there's like another dimension for like the validator set, like recurring fee. You can still think about it this way, like even if we don't do like multidimensional fees for normal transactions, you could imagine you have 2 fee dimensions rather than the 5 that are currently specified, and that wouldn't impact the block packing algorithm because you essentially have 2 completely independent constraints. So you could still think about it that way. Like it could be like a partially, like, you know, like a simple 2-dimensional. It's if you could actually look at it very much akin to like Ethereum's current mechanism, where they have the blob fee and the normal like gas fee, where they're not really considered multidimensional because they're actually two fully set independent dimensions, which is kind of confusing, but a similar kind of mechanism could work here if we wanted to.
And actually, what's interesting is if you index the P chain, the 4 dimension that I listed before, they're actually pretty correlated, right? So you can imagine the large transaction now, they have many UTXOs too, and they entail verifying a lot of signatures. So they're not, they're kind of pretty high correlated. Now, the validator set, say, fee scheme might be pretty orthogonal to that. But the first 4 of them, like even a single dimension fee rate, I don't think it would, strive that far away from the multi-signature one, practically speaking.
Yeah, I think a big reason why we really like multidimensional in the world of like HyperSDK is because it lets you juice like performance out. So you're like maximizing your utilization on all of your like independent constraints. But I think as we talk about on the P chain, we're maybe less concerned about juicing out the absolute maximum level of like performance out of our capacity. So yeah, I think based on this convo, it seems pretty reasonable to split out the multidimensional and dynamic mechanism. I think we're pretty much at time here too. I don't know if there's.
Yeah, I was going to close it out saying that we're definitely going to hold another meeting to continue the discussion on multidimensional fees. But as far as it goes for the dynamic fee, I personally feel that that's in a good place for us to kind of finalize that specification as well. And then excitingly begin work on everything that's been specified in ACP-77. So I think that this was a really, really fruitful discussion. And I want to thank everybody who joined us, especially those members of the community. If anybody has anything else outstanding, the discussion on GitHub is always like the best place to post any of your thoughts, feelings, concerns, questions, or, shower thoughts, like whatever you want, just put it in there and we'll probably answer it. But thank you all for coming. Thanks to the platform team, and thanks Alberto for such a good explanation of the ACP. And we'll see you guys next time. Thank you.
Thanks.